Hello, everybody. Glad you could tune in to the last session of the day. My name is Ilyan Georgiev from Autodesk. I hope you've been enjoying this year's conference from the comfort of your home with the tuxedo safely tucked away in the closet. So we'll see two papers today tackling opposite ends in the global illumination spectrum, namely caustics and diffuse lighting. Don't forget to post your questions in Rocket Chat, which you can do during the presentation already. If you have an amazing question, but no access to Rocket Chat, you can post it on YouTube, by exception. Let's dive right in. The first paper is on inferring photon density estimation kernels from deep neural networks. The talk will be given by Shilin and Zexiang, who will also be happy to take questions after the talk. And with no further ado, let's go.
Welcome to this talk. My name is Shilin. Today I'm going to present our EGSR paper, Deep Kernel Density Estimation for Photon Mapping. Computing global illumination is crucial for photorealistic image synthesis. For example, to render this scene with a glass object standing on a diffuse surface, we can use path tracing algorithm. The path tracing algorithm starts by shooting rays from the camera into the scene. When the ray hits the surface, a reflection ray is computed, and we keep tracing the new ray. And when the ray hits a transparent object like this, it can be reflected or refracted into the object. Finally, when the ray hits the light source, we can then estimate how much radiance can be transmitted from the light source to the camera. Following the same process, millions of camera rays can be traced. With sufficient number of rays, this algorithm can synthesize image well, with small Monte Carlo noise for most cases, and people have made great progress on denoising path tracing results. However, there's a problem with path tracing, that is, many rays do not hit the light. For example, this blue path will miss the light source. This will waste our computing power, since those paths contribute nothing to the pixels. And this is what we get if we render this scene using pure path tracing. And this is the result after applying the denoising. On the diffuse surface, we can see the caustics, which is shown here. And this is the ground truth caustics. I'm going to switch back and forth to let you see the difference. So this is mainly because it is difficult for the path tracing to successfully sample the path that goes through this glass ball and reach the light. Even with denoising, the caustics cannot be rendered efficiently. The problem becomes more severe when the light source becomes smaller. And this is when photon mapping method works very well. For the light specular paths, where paths interact with specular surfaces before arriving at light, photons are emitted from the light and traced within the scene. We keep tracing the photon until when the photon hits a diffuse surface, we store the photons on the surface. And millions of photons can be traced in the same way. After we finish emitting the photons, they are stored on the surface, as represented by these pink dots. Then we shoot camera rays. When the ray hits this diffuse surface, we find the nearby photons within some radius, or just using k-nearest neighbor search. The neighboring photons are used for reconstructing the radiance going to the camera from that shading point, and this is what we can get from simulating the light specular path using photons. Look how sharp the caustics are. This is because there are a lot of photons in the caustics region. More nearby photons usually means better reconstruction. For other paths that do not interact with specular surfaces, the low sample count path tracing with denoising is sufficient to find this path and reconstruct the radiance. Combining these two methods together, we can get this good-looking rendered image with beautiful caustics. So the photon mapping can provide a huge benefit for things like this, with strong caustics compared with path tracing. However, the major problem of photon mapping algorithm is that you need a lot of photons to reconstruct such a high-quality caustics. For example, this image is rendered with about 3 million photons. Neighboring search can take a lot of time, and the memory usage is a lot. Therefore, we really want to reconstruct caustics as quick as possible without using too much memory. Our target is to render these things with significantly less photons. This is the ground truth result of the same thing. Now I'm going to give you a quick performance comparison to give you some sense. These are the results of path tracing with 1000 samples per pixel, with and without denoising. It can take about 20 seconds to render, and even that, the caustics are still not good enough. And this is results using traditional photon mapping method. You can see the results look blurry and caustics are not sharp enough. These are two advanced photon mapping algorithms, stochastic progressive photon mapping and adaptive progressive photon mapping. For SPPM, the results are blurry, and even for APPM, we need about 1.5 million photons to get this good quality result. And this is the image generated by our method. Here we use only 15K photons plus path tracing and denoising, and we can reconstruct the caustics almost perfectly with less than 7 seconds. So in this work, we will present the first deep learning framework for particle-based rendering. And as you saw, we can render high-quality caustics with fewer photons and less time. Learning-based Monte Carlo denoising has significantly improved path tracing results, and our work extends these benefits to the popular photon mapping method. I will now introduce the method. Before I introduce our main method, I'm going to first explain the core module of photon mapping, radiance reconstruction step. After we emit the photons, we shoot camera rays and find the neighboring photons. The outgoing radiance from that surface point to the camera is computed by aggregating those photon power, which is tau. N is the total number of photons emitted so far, and K is the kernel function providing weights for photons. We observe that kernel selection is very crucial in this formula. The simplest kernel is the box function, which just averages photon contributions. There are more complicated kernels available, such as Gaussian function. Generally speaking, the kernel function just provides weights to the photons. It is known that neural network is a universal function approximator, so why not use neural network to represent this kernel? However, using neural network to participate in the radiance reconstruction is not easy. First of all, we all know that neural network behavior is hard to control, and sometimes it can even generate noise. Second, the input photons can be very diverse in terms of position, direction, and power. These problems can greatly affect training stability and the test generalization ability. To make the network more controllable, we design and train a neural net that directly outputs the kernel value for each photon and using the standard formula to reconstruct the radiance. In this way, the network understands that its objective is to learn weights to combine photon contributions, and it knows the radiance must be calculated using this formula. The input to the network is also carefully processed to stabilize the training. For each shading point, we query and obtain these neighboring photons. We first convert photon data such as position and direction to the local shading frame. This will greatly improve the generalization of the method, since no global value is used. For each photon, we collect its local position, local direction, and power. To stabilize the training, the position is normalized by the search radius. The power is then converted by a nonlinear range compressor, since neural networks are not good at handling data with large range. So what does our network look like? Let's go into the detailed architecture. Like I said, we first query and pre-process the neighboring photons. Then we have this photon statistical data in the local shading frame. We first extract features from the photons by going through a multi-layer perceptron with several fully connected layers. Then we add a pooling layer with both max pooling and average pooling to obtain the global deep context features. The deep context feature vector is then concatenated with extracted features. And the combined feature goes through another group of fully connected layers. This last layer outputs the kernel value for each photon, and we reconstruct the radiance using this standard formula. This is very much like a simpler version of point net, which is widely used in computer vision community. Applying this point net-like architecture to photons is very natural, since photons are just like point clouds. If you expand the modules, this is the detailed architecture of our network. You can refer to our paper to see the details. We train our network with our own procedurally generated random training data. You can see we randomized the albedo color, the objects, the material, and area lights. Most of scenes contain at least one transparent object, which is necessary for generating caustics. Because our network focuses on local photon distribution around the shading point, our training data is actually highly diverse. Therefore, our network can generalize well to these test scenes, which are very different from the training scenes. As for the loss function, we just use a normal L1 loss on final renderings. However, the HDR pixel value can hurt network training stability. So just like previous denoising works, we apply a similar range compression function to the HDR output before computing the loss. Here, V is the input value and P is the output value, and mu is set to 5000. This function effectively reduces the range of data. We run all of our experiments using optics ray tracer. Also, the denoiser used in our paper is also from optics. We use a desktop with a 32-core CPU and 2 GPUs. We train two versions of our neural network, a smaller one with 32 feature channels, and a bigger one with 128 feature channels. We tested on 6 different scenes with strong caustics effect, with different number of photons. As I mentioned in the beginning, all of our renderings are generated by running our method on that specular path, and running other paths with regular path tracing. Then we add them together. We use PSNR and SSIM for quantitative comparison. The first experiment is to test the effectiveness of the kernel. Hope you still remember we use a neural network that takes photon statistical input and output kernel values. However, there is an alternative way to reconstruct the radiance. Besides kernel prediction, we can also directly estimate the outgoing radiance. Then the output of our neural network will be the radiance, and this is the naive solution. In this case, the standard formula is thrown away and replaced by the neural network directly. So the question is, which way is more efficient and more robust? To answer this question, we train both two networks for 1000 epochs and see how they predict. This is a prediction from our kernel estimation framework. And this is a result from direct estimation framework. The conclusion is obvious. The kernel estimation framework produces much better results. Moreover, using kernel is more robust since the network can only implicitly control the final pixel value. Direct estimation gives neural network too much freedom, and this can be dangerous since it sometimes generates low-frequency noise. Now let's first compare with path tracing. I use these two scenes as examples. These are ground truths generated by running both photon mapping and path tracing for a long time until convergence. And these are rendered with path tracing with denoising and 1000 sample per pixel. Even with Monte Carlo denoising, the caustics still look bad. And without denoising, path tracing result is very noisy, and you cannot even see the structure of the caustics clearly. And these are our generated results, which is shown in the red box. They are obviously closer to the ground truth. Now we compare against other photon mapping methods, including standard photon mapping using k-nearest neighbors, SPPM, and APPM. Here we use this red Wann thing as an example. These are ground truths. These are the standard photon mapping with 50 and 500 neighbors. You can see that results are blurry if setting the k too big, since the faraway photons are also taken into account in radiance reconstruction step when k is too big. These are SPPM and APPM results. These advanced methods are progressive and more robust to the number of neighboring photons, but they still have some gap compared with ground truth. These are our results using 50 neighbors. The predicted kernel of our neural network really makes the caustics very sharp. As I mentioned, we have a smaller network with 32 channels and a larger one with 128 channels, and both works reasonably well as shown here. These are our results using 500 neighbors. These are also better than other existing approaches. We further run SPPM and APPM with more photons, which is 8.5 million here. And APPM looks comparable to ours, but SPPM is still blurry. This means that our method produces equal quality results with significantly less photons. There are other examples seen showing the similar comparison in the paper. The conclusion is that we can reduce the required number of photons by a few times. Let me quickly go through other comparisons on other things we tested. These are the ground truth zoom-in view of the cropped regions. And these are standard photon mapping results. With 500 neighboring photons, results are blurry. With 50 photons, results contain a lot of noise. These are SPPM results. SPPM looks better with 10 times more photons. However, the reconstructed caustics still lack some details. And these are our results. Because we are using a neural network to represent the kernel, it can generate a detailed caustic structure without introducing extra noise. Given the local photon context, our network learns which photon is important and which photon should be almost discarded. Let me now show the quantitative comparison. Here we use mean squared error metric on pixel values to show the difference. We test each thing here with different numbers of photons. For example, for this glass egg thing, the number of photons ranges from 15K to 1.5 million. These columns are baseline algorithms. The yellow ones are the best baseline methods with the lowest MIC error for each setting. And these are MIC of our method. The red ones represent the lowest error, and the purple ones represent the second lowest error. From the numbers, you can see our error is much smaller compared with baselines for all of our tested things. We tested 6 different things in total, and the conclusion is the same for all the things. Our method significantly reduces the error for the final rendering. Finally, let me show the timing of our modified photon mapping method. This table provides the running time for photon tracing and gathering of different number of photons. And this table shows the network running time for inferencing one 512 by 512 image. In other words, the network processes 512 by 512 shading points. As shown from our results, even our small network can outperform baselines, so it is not always necessary to run a large network with large number of neighboring photons. Here we just offer some network choices, and users can pick a proper one for their specific needs. We think there are several next steps that can be done in future research. Currently, our network is trained on a fixed number of neighboring photons. The machine learning community has provided some progressive training framework, so it will be interesting to see if we can train this network in a progressive manner, which can generalize well to arbitrary number of neighboring photons. We haven't explored the network compression or other architectures other than PointNet. Also, it is interesting to see the produced results are temporal stable for animated scenes, although in the paper we have shown that it is stable with camera view change. Currently, we only have 500 simple random scenes for training, So I think you may get a network with better performance and better generalization if it is trained on massive industry data. Finally, our method simply swaps the kernel density estimator, which is actually orthogonal to many radius reduction frameworks. In this work, we presented the first deep learning framework for density estimation in particle-based rendering. We introduced a deep neural network that learns a kernel function to aggregate photons at each shading point and renders accurate caustics with significantly fewer photons than previous approaches, with minimal overhead. Learning based on Monte Carlo denoising has significantly improved the path tracing results, and our work extends its benefits to the popular photon mapping method. This is the end of my talk. Thank you.
Well, thank you for the great talk. Looks like people have paid attention and they have some questions on the channel, so that's good. I'll start with Pascal Gritman, who's asking if you've tried giving some additional inputs to the training, to the network, for example, surface normals or albedo, any of the typical auxiliary information.
Okay, that's a good question. For the surface normal, actually, for our method, we first convert all the photon information like positions and directions to the local shading frame. So we didn't use the global coordinate system. We used the local coordinate system. So the surface normal will be just like the z axis in the local shading frame. So we didn't include them because they're all the same vector. As for the others, we concatenate the photon position and direction, and we also have the photon power. And the BSDF is included in the radiance reconstruction step. So we also don't include them into the network. So the network only takes the photon statistical data like position, directions, and power.
Okay. Tobias Rachel is asking if this can be, the rendering method can be made progressive.
Yeah, that's also a very good question. We currently we're training our network using the fixed number of neighboring photons, because this will give us the best results. So currently we have two networks. One is trained on 50 photons, and another one is trained on 500 photons. Of course, this can be made progressive if we can you apply some progressive training framework so that the network can be applied to any number of neighboring photons. But that will include some new method and like the progressive training method. So currently we think this is an interesting next step to do, and we leave it as a future work.
Okay, thanks. Wojciech Jarosz is asking, what do you think would need to change to extend this approach beyond what you've tested it on? For example, non-caustic effects or very complicated scenes with displacement maps, participating media. It's a complex question. I also was wondering the same thing. So you focus on caustics, as I understand, and you leave it to path tracing and image space denoising to handle the remaining illumination. But could you see this method being extended to handle more general setting?
Okay, that's a great question. Firstly, in this work, we mostly focus on caustics because we have a huge benefit on using network on reconstructing the caustics. And for the non-caustics region, we also tried to reconstruct the radiance, and actually it can generate just similar comparable results with path tracing with denoising for those non-caustic regions. So for those regions, you can just use path tracing plus denoising. That will give you good reconstruction with small amount of time. So we think this is the best, from our perspective, it's the best combination, combining the path tracing result with the photon mapping result that generates the caustics. And for the others, more complicated things like participating media and the non-caustics effects, we haven't tested them. But currently, our network it's just works like a kernel density estimator. So what you have to do is just to swap the kernel estimator. That's all you have to do. So it's easy to test this method on different things and different effects, and we will include them in the future works. Yeah.
Okay, thanks. And Wojtek was also asking if you know how well your training generalizes to effects or types of scenes that are very different from your training data. So basically, if you train on one thing, but you feed some very different, like, I don't know if he's asking if the training set is representative, or rather how well it extrapolates to cases that he hasn't seen. What's your experience with that?
That's a great question. In our work, we train, as we presented in the slides, we trained on 500 randomly generated things. And each thing contains some caustics, and also we randomized the albedo color, the position of the object, the material, and also the light, the area lights. So because our training data is on each shading point, because each shading point will query the neighboring photons. So actually for each thing, we have a lot of training data, if you think of that way. Mm-hmm. So we have 500 trainings. Actually, the number of data is quite huge. And we tested on these 6 different things, which are very different from our training things. And currently it works well. I think it's mainly because we train our network using a very highly diverse training data. But obviously, you can improve. You can always get more data and train the network for more data. So yeah, I think currently the network generalizes well because we're using the kernel estimation framework. So the network will not directly change the output value or pixel values. What the only thing it can do is to output the weights for the photons, which is the kernel. So this makes it very robust, and the generalization is very good.
Oh, thanks for the answer. And 2 more related questions. So I was wondering, how big is the trained network, and is it then fast enough to do real-time rendering of caustics, which is asked on the Rocket chat by Daki.
Currently, we have 2 versions of the network, so 2 sizes. So we have the multi-layer perceptron, so which contains a lot of fully connected layers. So for the small network, we use 32 feature channels, and the larger network contains 128 feature channels. So as presented in the slides, we show the timing, and the smallest timing for rendering one 512 by 512 image can be 0.3 seconds, but for the very large network, it can go up to 10 seconds. So this, but the larger network will always use the slightly better results. So we just offer some different choices, and if you really want to make it very quick, you can use our small network, which can run in like 0.3 or 0.4 seconds. So although it's not like can run in real time, like 30 frames or 60 frames per second, but I think it's pretty good compared with existing standard photon mapping method, which needs a lot of photons for at least several minutes or even hours to render.
I see. I think it's kind of related to how you want to implement it. So for this paper, we didn't meant to optimize it very hard, because in our case, actually, we separate the rendering to path tracing and the photon mapping. The path tracing with denoising, in our case, it takes 3 to 5 seconds. So we use photon mapping for only about 1 second. It's already very fast. I mean, if you want to do real time for very challenging scenes, you also need some real-time path tracing algorithms, and then probably you want to like optimize the photon tracing and photon gathering steps. Then the network itself is actually very fast, so it could potentially enable some real-time applications. Yeah.
Thanks. And we're almost done. I had a question I really wanted to ask. Last thing. So there's been a lot of work on bias control for photon mapping, for example, based on adaptive adjustment of the kernel support, on counting photons inside subregions inside the kernel support. A lot of work. And I was wondering, what's the advantage of your neural reconstruction approach compared to those prior works? Have you tried anything?
We observed that our neural network has a very huge gain on the boundary of the caustic, especially when the boundary of the caustics have the within the shadow region. So this means the network takes the local photon features. So the network learns which photon is important and which photon is not important, based on the feature we give it, like the position, the direction, and power. So the network observe this kind of data in the training set. So during the testing, the network can sharpen the boundary of the caustics based on what it looks like for the neighboring photons. So this is something that is nothing may not be explicitly encoded in some typical functions like Gaussian or something like that. So we think the network learns something better, so they can make best use of the local photon information.
Okay. Yeah.
And in some sense, sorry.
Oh, no, please.
In some sense, we observed that we are normally using 500 nearest neighbor photons. And if you send that large amount of photon to some photon mapping algorithm, it will usually blur the results. But the network seems to kind of easily tell which photons it should use because it's predicting kernels. So in some sense, I think the network implicitly learns some bandwidth or some filtering it believes it's the best to select the best photons. So I guess it's also related to the traditional bandwidth reduction or other methods. But yeah, I guess in this case, the network learns to kind of select those things. Yeah.
Right. It's a data-driven approach. Yeah.
Mm-hmm. Yeah.
Okay. Thanks again for the nice Q&A. We need to move on to the next talk, which is called Adaptive Matrix Completion for Fast Visibility Computations with Many Light Rendering. It will be given by Sunrise Wang. And again, he'll be taking questions after the talk. Please post them on Rocket Chat or on YouTube. Let's start the video.
Hello everyone, and thanks for attending this presentation. My name is Sunrise, and I'll be talking about using adaptive matrix completion to approximate visibility in scenes with large numbers of lights. So the problem we're trying to deal with is the many lights problem, which involves the direct rendering of scenes with large numbers of lights in them. A typical occurrence of these types of scenes is when using the instant radiosity algorithm, as it approximates the indirect lighting of the scene with a set of point lights. So these scenes can have a very large number of point lights, ranging from thousands to millions. For example, all of these scenes to the right here were rendered each with 100,000 point lights. And this can, of course, be very expensive to evaluate, as we need to not only evaluate the shading between every light and every pixel, but we also need to determine if there's a line of sight between them by typically through raycasting. So this paper presents a method or a framework to allow for the fast rendering of such scenes. It achieves this through the use of clustering and visibility approximation. The core contribution of this paper is the use of the adaptive matrix completion algorithm to approximate this visibility information. And also we look to introduce some improvements to this algorithm in order to specially tailor it for the problem of visibility approximation. So there have been quite a large number of methods already that aim to evaluate these lights in sublinear time. For example, you get methods that look to hierarchically cluster these lights into some tree and then traverse a tree in order to extract some clusters. You also get methods that formulate the problem as a matrix and then subsample this matrix and using that information cluster the lights. And also, so we're also interested in this matrix formulation. So this matrix is typically called the many lights matrix and can be structured as seen here, where you have lights as the columns and receivers as the rows. And each cell essentially represents the shading that that specific light gives to that respective column. So this matrix is interesting because it's approximately low rank, which means that most of its information lies within a few basis vectors. This means that it's both compressible and that it can be mostly approximated by just partially observing it. And there has been quite a bit of work that looks to take advantage of this already. For example, the work of Wang and colleagues that use a generalized Nystrom method to complete the matrix for inverse rendering purposes. There's also the work of Ho and colleagues that look to use low rank and sparse matrix recovery to remove the error from an approximated version of this matrix. And then there's also the work of Ho and colleagues who use low rank matrix completion to complete a participating media variant of this matrix. So in our work, we're also interested in the problem of low rank matrix completion. And the problem can be seen here, where you have some matrix with partially observed coefficients. And the idea is to essentially infer the missing values. And of course, this can have many to infinite numbers of solutions, as you can just put in whatever values here. So typically, there's an additional constraint that we are looking to get back the matrix with the simplest matrix explaining the initial observations. And in matrix terms, this typically refers to the matrix with the lowest rank. So this is a relatively new field, but there has been quite a lot of work already been done on it. For example, there are nuclear norm minimization algorithms that can achieve that can solve the problem, as well as alternating least squares algorithms, and also various low-rank approximation methods can also be used. And central to all of these methods are some matrix properties that essentially determine how many initial observations you need in order to accurately complete this matrix. These properties are the rank, which can be thought of as how many linearly independent dimensions there are in the matrix, and coherence, which can be thought of as how localized the matrix features are. So one can, of course, look to naively apply one of these matrix completion algorithms to the many lights matrix, but you would have to typically limit the many lights matrix to be of low rank, which in practical terms means that you're limited to things, scenes such as diffuse scenes or scenes with a lot of participating media in them. So the reason for this limitation is because it's very difficult to determine the rank and coherence for arbitrary scenes, as you have many factors influencing these values, such as material and geometry. To give an extreme example, if you have a scene with fully specular surfaces, you'll essentially end up with a full rank matrix, which needs full sampling in order to be completed properly, and matrix completion cannot actually be applied to that matrix. So we choose to formulate the problem slightly differently by separating the many lights matrix into two different ones. So one is a shading matrix, which contains all information or shading information other than visibility, and a visibility matrix, which contains only Boolean visibility data. So to get the many lights matrix from these two matrices, you can then simply perform an element-wise multiplication of them. So the advantages of formulating things this way is that this shading matrix only relies on local information and can be very easily parallelized. So we can actually just fully compute it quite quickly by just putting it on the GPU. In terms of the visibility information, this would actually require ray casting and is essentially the bottleneck of the process, and thus it makes sense to only partially compute this and complete it. Also, by only completing the visibility information, we discount the material's influence on the rank and coherence of the matrix. So this means that we can apply this method to a wider variety of scenes. And also finally, the visibility matrix is Boolean, which allows us to make some improvements to the original matrix completion algorithm, which improves both the performance and accuracy. So our framework is shown as follows. So our framework is implemented in the context of instant radiosity, so we generate some virtual point lights, and we do this by randomly sampling paths from emitters and then using the vertices of these paths. Afterwards, we generate receivers by casting rays into the scene. And then we slice these receiving points based on both their positional and orientation information. And we do this because it both simplifies the completion process, and also it allows us to have fewer clusters, as we can now extract clusters per sample, or per slice, rather than clusters for the entire scene. So for each slice, we then cluster the VPLs. For this, we use a modified version of the light cuts algorithm, which operates on slices rather than single pixels. Afterwards, we approximate the visibility using matrix completion, and at the same time, we fully compute the shading information. And then we combine this information to form the final render for the slice, after which, after we finish computing every slice, we can then combine all of the slices to create the final image. So all of these steps shown in gray here are done on the CPU, and the step shown in red is done on the GPU. And all of these per slice steps are pipelined so that we make full use of both the CPU and the GPU at any given time. And so the core contribution of our paper is this step here, which is the approximation of visibility using matrix completion. So I'll be essentially spending the majority of the rest of this presentation talking about this. So the matrix completion algorithm we use is the adaptive matrix completion algorithm, and I'm not going to detail or give the full details for this algorithm here, although our paper does contain the full details for those of you who are interested. But here I'm just going to give a very high level intuition behind the algorithm. And essentially the idea is that we have some matrix that we're looking to complete and some basis, some set of basis vectors. And the idea is that we look to iteratively complete this matrix by subsampling the columns. So we subsample a column of the matrix, and then we see if the basis can represent it. And if the basis vectors can represent it, then we can just use the basis vectors to complete the rest of the algorithm. Of course, if the basis vectors cannot represent this subsample column, then we fully sample the column and add it to the basis vectors. So the idea here is that it essentially does an adaptive sampling on the columns of the matrix, which means that it relaxes the row space coherency constraints. And furthermore, another benefit of this algorithm is that it does most of the operations actually on the basis vectors, which means, well, these basis vectors are typically a lot smaller than the full matrix, which means that this algorithm is often cheaper than other matrix completion algorithms. One drawback to this algorithm is, however, that it needs a pseudo-inverse operation. And this operation is essentially needed to get some coefficients in order to find out how we can best linearly combine the basis vectors in order to try approximate some incoming vector. The thing is, if there are a lot of basis vectors, or the basis vectors are very large, this algorithm can be very expensive. The pseudo-inverse operation specifically. And it can actually very easily get to a point where running this algorithm is much more expensive than just fully evaluating it. So our aim is to get rid of the pseudo-inverse operation. And we do manage to do this and replace it with some Boolean matching algorithm. But to essentially give an intuition about why this Boolean matching algorithm works, we have to have a look at the visibility matrix, which can be seen here. So this is taken from one of the slices in one of our scenes, with the low rank areas being boxed in blue. And as can be seen here, the cause of the low rankness is essentially from a bunch of columns having the same visibility patterns to the receivers. This implies that actually, instead of trying to find some linear combination between the columns in order to approximate some incoming column, what we can instead do is just try to use a single basis column to approximate it, which is essentially what we do. With the matching algorithm, you can essentially check which basis vectors match the incoming subsampled column, and then simply just use those vectors to extrapolate on those matching vectors in order to reconstruct the column. So you only consider one vector here. And using this Boolean matching algorithm is advantageous because it is order mn rather than order mn squared, which means that it should scale a lot better to different sizes of bases. So to validate this method, we compare it to both the original pseudo-inverse method as well as Gauss-Jordan elimination method, which is essentially there to find coefficients for Boolean matrices. So here we compare the performance of the method when varying the number of columns and number of rows, and the matching method, as seen in green here, can be shown to perform both better and scale a lot better than both of the other methods. Of course, the simplification can introduce error. So in order to see how much accuracy we lose, we plot the total samples versus the error for all three methods across a couple of different scenes. And we found that actually we don't really lose any accuracy when using the simplification, which is great because it allows for a significant performance increase given no accuracy loss. So another problem with the original algorithm is that when subsampling the columns of the matrix, it uses uniform sampling. And this is bad because it means that the column space coherency constraints will apply. So instead of doing things this way, we look to importance sample these columns. And so the idea is to essentially assign more samples in spaces where visibility changes a lot. This is of course quite difficult to determine. So what we are essentially so this is quite difficult to determine, but because the completion algorithm is done in a column-by-column iterative manner, we can actually use information from previous columns to drive the sampling of new columns. So essentially, we just maintain some distribution D, and then update it whenever a column is fully sampled with the appropriate probabilities. And we found that this works, this improves renderings in scenes with small occluders, for example, the San Miguel scene here to the right, which has a lot of leaves. So the top here is the San Miguel scene with uniform sampling, and the bottom is with importance sampling. And as can be seen, there are a lot less visibility artifacts. And also, it should be noted that I upped the brightness and contrast of this image just to make these artifacts a bit more visible. So to validate our method, we tested it over 12 scenes of varying complexity, using virtual point lights in diffuse scenes and virtual spherical lights in glossier scenes. And our ground truth images are obtained by brute force evaluating all of the lights. So we compare our method to three other rather well-known methods in the field, and as well as our method without any visibility approximation. So I'm not going to go into the full, show the full set of results here, nor am I going to go into any detailed analysis, but all of this can be found in our paper and supplemental. I'm just going to show three scenes here. So the first is the bathroom scene, which is one of our glossier scenes, rendered with virtual spherical lights, and this took 185 seconds with 23% of the visibility samples. The second scene I'm going to show is the San Miguel scene, which is one of our more geometrically complex scenes. And this took 125 seconds to render at 16.64% visibility samples. And finally, there's the sponsor scene, which is one of our simpler scenes in terms of visibility. And this took 140 seconds to render at 11.81% samples. And to just give an idea of how our method improves upon previous methods, so I'm just going to show the some equal time error images, L1 error images, of our method compared to the method of the low rank and sparse recovery method of Wann and colleagues. So this first error image is the one obtained from the method of Huang and colleagues, and the second is from our method. And as one can see, it's a significantly lower error. So to give an idea of where we need more samples in the scene, it's essentially in areas of penumbra, as this is essentially what causes high visibility rank. And to give an idea of why this is the case, I just extracted the visibility matrix of one of the slices lying in penumbra in the San Miguel scene. And as one can see, the penumbral region is essentially caused by a lot of lights having slightly different visibility to the receiving points. And this essentially results in a very high rank area, which needs a large number of samples to be able to complete accurately. And also to give some insight of how the visibility matrix compares to the many lights matrix in terms of rank, we typically found that it is higher rank in diffuse scenes, such as this scene here, but it is lower rank in glossier scenes, which is roughly to be expected. So in terms of drawbacks to this method, the first is, so if you can recall, every time a column cannot be fully represented by the basis, we fully sample it. But this can of course be quite inefficient because it could only be a small part of the column that can't be represented. So of course sampling the entire column can be inefficient. So to deal with this problem, we could actually just look to investigate some partial sampling method, which just samples the incorrect part of this column. Another drawback to our method is that our clustering method doesn't take into account visibility, which results in suboptimal refinement in certain areas. This is made very obvious when rendered with glossy surfaces, as shown in the above image here. So in the bottom, we switched to a clustering algorithm that actually takes into account visibility, that being light slice. And as can be seen, there is a drastic improvement in the quality. So in conclusion, in this presentation, we introduced a method for speeding up the rendering of scenes with large numbers of lights. This method achieves this through the use of both clustering and visibility approximation. Mainly, our main contribution is this approximation of visibility using the adaptive matrix completion algorithm. And finally, we also introduce a variety of improvements to this algorithm to specially tailor it for the problem of visibility approximation. Also, I didn't actually mention this earlier in the presentation, but our method achieves essentially a 3 times speed up roughly over other methods for same quality renders. So in terms of future works, there's of course a need to address the drawbacks discussed earlier. But in addition to this, and a relatively straightforward extension of the algorithm is to area lights, because there isn't really a limit to how many columns we're looking to add. So for every new point in the light, we can just add a new column. We also want to look into the integration over other domains such as time and spectrum, because currently when you add a new domain like this, there's going to be an explosion of matrix size, which pretty much invalidates the use of this method. And finally, we want to look into using matrix completion in other rendering contexts, such as path tracing and denoising. So thanks everyone for listening and attending this talk. I will try my best to answer any questions if you have any right now. Thank you.
Hey, thanks for the nice talk. Let's do some questions now. There's Wojtek Jarosz on Rocket Chat asking, so if you have a shading point that's and you consider a connection to a VPL in the bottom hemisphere, so illuminating it from below, the contribution is 0, but that contribution could be considered to be either due to no visibility or due to 0 shading. So there's a choice. Where do you put that 0? Have you thought actually what gives better results in that case?
Yeah, so for this in our work currently, it's represented in both the shading and in the visibility matrix, because currently our shading and visibility matrices, they correspond directly to each other. In order to, but yes, in order to save on memory, we could perhaps just get rid of the information from actually from both matrices, since the result would be 0 anyways. But yeah.
Okay, thanks. I see someone else typing, and in the meantime, I was wondering, so the fact that you fill this matrix, it wasn't clear whether it produces a biased or an unbiased approximation to the result, and what is the quality control then?
Right. So with regards to, well, it's currently our work operates on the instant radiosity method, so there's some underlying bias there. But with regards to this matrix completion, it tries to recover the actual original visibility information as closely as possible. So it's difficult to yeah. So the more samples you would give a column, the more closer to the correct visibility value it would be. So I don't know if that answers your question.
Actually, a simple question would be: does it give an unbiased estimate? So, I mean, sorry, if you ignore all the bias inherent to instant radiosity, would you still have an unbiased solution, or?
Yeah.
Okay, thanks. Murat Kurt is asking on Rocket Chat, what's the average PSNRs in the difference images? So basically, he's asking for some numbers, error numbers.
So they're shown. So it depends on the scene. For example, some of our glossier scenes, which we tested using virtual spherical lights, we actually found that once we clustered, we lost a bit of energy. So there it could be so we used RMSE for that for our error metric, and it could get as high as maybe 0.1. Yeah, and with regards to the diffuse scenes, so for simple scenes like the corner box, it very easily gets to like 0.00. Let me just check actually. I'm not sure now, but yeah, it's
well, I guess if you have numbers in the paper that.
Yeah, it's most of the numbers are in the supplemental. Yeah.
In the supplemental. Okay,
yeah.
Good to know. Someone else is typing a question, and in the meantime, so back to the error again. So there seems to be a trade-off in the initial clustering. So a smaller number of high. So basically, if your initial clustering is coarse, you'll get, as my understanding, a small number of higher rank matrices. Or if you do a fine clustering, you get a larger number of small and lower rank matrices. Is it clear actually where the sweet spot is and how to find such a sweet spot in the cluster?
Yes. So currently, actually, if you have a small number of clusters, your rank will probably be relatively low, because a small number of clusters essentially causes a lot of hard shadowing in the scene, which inside the matrix just manifests itself as like a lot of contiguous regions, and not the smooth variation that I showed in one of the last slides. And so this is actually quite the algorithm works quite well here. The issue is so when you have more clusters, it actually raises the rank slightly. Of course, you can sort of compensate theoretically by increasing the number of receiving points inside of your matrix, but so because we do the full sample for every column, whenever it can't be represented by the basis, this tends to not scale particularly well here. But we're looking into ways to just partially sample the column in the places where it's incorrect. And if we get this working properly, then yeah, this could be a way to essentially counteract the trade-off. So we could probably find a way to adapt the size of the receiving points based on how many light clusters we have.
Yeah, okay, that's interesting. Let me see. One thing regarding these approaches based on clustering and animation renderings, because when a light, you use all the same set of VPLs for the entire slice, you can get some banding artifacts in the image that can be apparent when in an animation. So I was wondering if this can be alleviated with some sort of, say, randomization in the matrix, just to introduce some noise in the matrix that will basically manifest as noise in the final image.
So maybe if we were dealing with the original many lights matrix, this might work, but I think introducing some noise inside the visibility information could be quite dangerous, because you could very easily get very obvious visible like artifacts if, for example, a light with high intensity is just like its value is perturbated. Although with regards to the banding that you brought up, although this is an issue, we found from our tests that using like these light cut based methods, it typically did not introduce like very noticeable banding effects with regards to at least from what we see in our test scenes. But yeah, to answer your question, I don't think at least for using visibility this way, it could we could get rid of the banding. But maybe if we introduce a noise into the shading information, that could that might help.
Thanks. Regarding the shading, actually, I was also wondering if, since you compute the shading independently, assuming full visibility, you can end up over shading in regions that are, say, occluded. Could this be a problem?
Sorry, what do you mean overshade? Or do you mean like just computing too much?
Right. So if you speculatively compute shading for connections that will end up being occluded, if you do this if you do the shading independently from the visibility, and you only at the end multiply the two, you may end up over shading.
Yes. So actually, the way we implement it is because it's pipeline. So the actual visibility approximation of a slice happens before the shading, and so when we are shading for one slice, we're actually doing the visibility approximation for another slice. So essentially, when we're running the kernel for the shading, it already knows whether or not something is visible, so we can terminate early.
Okay, so shading is computed actually after the visibility computation for each slice.
Yeah.
Okay. Thank you very much. I think that was it. Unless there are any questions on YouTube, let me just move to my second screen. That's no. But again, thanks a lot for the nice and extensive Q&A sessions, both presenters. This was the last session for today, so wherever you are in the world, you either grab a beer or go to sleep, or a coffee or lunch, and have a good time, and I'll see you tomorrow. We'll have some more interesting talks. Thanks again, and bye-bye.